To get started, can you identify which of these triangles is equilateral? Exactly, this triangle is equilateral, meaning all its sides have the same length. For this equilateral triangle, suppose each side has length 2. Let's see if we can figure out this triangle's area. We already know the base of this triangle is 2, so to find the area it would really help if we knew this triangle's height. Now, if this bottom side has length 2, how long is this segment between the altitude and this vertex? Precisely, this purple segment is half of the base, so its length is 1. And you can prove that to yourself by showing this shaded triangle is congruent to this other triangle by angle side. So at this point, can you figure out the length of this triangle's altitude? Try applying the Pythagorean Theorem to this right triangle here. Excellent! The length of this altitude is the square root of 3. So now you know the base has length 2 and the height has length root 3. So then what's the area of this equilateral triangle? Right, the area of any triangle is 1/2 times the base, which is 2 for this triangle, times the height, which is root 3. And if we multiply this all together, the 1/2 and the 2 cancel out, leaving us with root 3. So the area of an equilateral triangle with side length 2 is the square root of 3. Nice. Next, let's find a general formula for the area of an equilateral triangle with side length s. Again, let's start by finding the height of this triangle in terms of s. Notice that these two equilateral triangles are similar. So can you use the ratios of these lengths to determine the height of this triangle? Excellent! So an equilateral triangle with side length s has a height of s times the square root of 3 over 2. So now that you know the base and the height, what's the area of an equilateral triangle with side length s? Nicely done! So the area is 1/2 times the base, which is s, times the height, which is s times root 3 over 2. And we can simplify this expression. Multiplying 1/2 and root 3 over 2 gives us root 3 over 4. And s times s is s squared. So the area of an equilateral triangle with side length s is s squared times root 3 over 4. So next, try using this formula you came up with. What's the area of an equilateral triangle with a side length of 6 centimeters? Give your answer as a decimal and round to 2 decimal places. Nicely done. Next, suppose you have a regular hexagon with a side length of 10. Can you figure out the area of this hexagon? And here's a hint, you can divide up any regular hexagon into a few equilateral triangles. Well done! First, you can find the area of one of these equilateral triangles with side length 10. It's 10 squared, or 100, times root 3 over 4. And this regular hexagon is made up of 6 of these equilateral triangles, so its area is 6 times 100 root 3 over 4, which equals 150 times the square root of 3. Okay, so this approach of using the Pythagorean theorem to find the height can also work for isosceles triangles like this one here, with 2 sides of length 3 and 1 side of length 4. So what's the area of this triangle? Okay, no problem. Let's draw in an altitude. Now for this isosceles triangle, this altitude bisects the base, cutting it into 2 equal halves, each of length 2. So try using the Pythagorean theorem to determine the height of this isosceles triangle. Excellent! The height is the square root of 5. So if the base is 4 and the height is root 5, what's the area of this isosceles triangle? Well done! This triangle has an area of 2 times the square root of 5. So for isosceles triangles, you can use the Pythagorean theorem to help you find the area. And for equilateral triangles, you might want to memorize that the area always equals the side length squared times root 3 over 4. In this lesson, we'll introduce Heron's formula, which is also known as Heron's formula. We'll start with a right triangle whose side lengths A, B, and C equal 8, 15, and 17. Because this is a right triangle, you already know its base and height. So first off, what's the area of this triangle? Right, the area is 1/2 base times height, so it's 60. Now Heron's formula is another way to find the area of a triangle, using a triangle's side lengths and perimeter. So first, what's the perimeter of this triangle? Exactly, the perimeter is 8 plus 15 plus 17, or 40. Now let's quickly define a new word, semiperimeter. For any polygon, the semiperimeter is half of its perimeter. So what's the semiperimeter of this triangle? Exactly. Since the perimeter is 40, the semiperimeter, which we'll call S, is half of that, or 20. So we're almost ready for Heron's formula. But first, try evaluating these three expressions, S minus A, S minus B, and S minus C. So we're taking the semiperimeter, 20, and subtracting each of the three side lengths. Right, so these expressions equal 12, 5, and 3. Next, let's multiply the semiperimeter and these three expressions all together. So we have S times S minus A times S minus B times S minus C. For this triangle, what does this product equal? Excellent, so 20 times 12 times 5 times 3 equals 3,600. That's a pretty big number. Finally, what's the square root of this expression? So what's the square root of 3,600? Right, it's 60. And that happens to be the exact area you found at the beginning. So this is Heron's formula. It's a way to find the area of a triangle when you know its three side lengths. For a triangle with sides A, B, and C, you can find the semiperimeter S by adding A, B, and C and then dividing by 2. Then you can use this formula to find the triangle's area. Let's try an example. Suppose you have a triangle with side lengths 13, 14, and 15. What's the area of this triangle? You can't calculate 1/2 base times height because you don't know the height of this triangle. But you do know the three side lengths, so try finding its area using Heron's formula. And if you need some help, feel free to ask for a hint. Very well done. Here's Heron's formula. The semiperimeter is half of 13 plus 14 plus 15, or 21. 21 minus 13 is 8, 21 minus 14 is 7, and 21 minus 15 is 6. And if you evaluate this square root, you get 84. So that's the area of this triangle. It's 84. Try another example. Given a triangle with side lengths 5, 5, and 6, what's the area? Again, all you know are the side lengths, so Heron's formula would be the way to go. Precisely. Again, here's Heron's formula. Now the semiperimeter is 8. 8 minus this 5 is 3, and 8 minus this 5 is also 3. And finally, 8 minus 6 is 2. Multiplying these numbers together gives you 144, and the square root is 12. So this triangle has area 12. Now because of the square root in Heron's formula, you'll often find that triangle areas involve square roots. So try another example, a triangle with side lengths 5, 7, and 8. Right, so this time when we apply Heron's formula, the semiperimeter is 10. 10 minus 5 is 5, 10 minus 7 is 3, and 10 minus 8 is 2. So this equals the square root of 300, and that's approximately equal to 17.32. Okay, let's look at one last example, and this one's a little tricky. What's the area of a triangle with side lengths 2, 3, and 5? Exactly. So applying Heron's formula, the semiperimeter is 5. 5 minus 2 is 3, 5 minus 3 is 2, and then 5 minus 5 is 0. So the product of all these numbers under the square root is 0, and the square root of 0 is just 0. So this triangle has area 0? What's going on? Well, this is what our triangle looks like. This side has length 2, this side has length 3, and they add up to the third side of length 5. This triangle is just a line segment, which you can also see using the triangle inequality. Remember, the sum of the two smaller sides should be greater than the third side. When they're precisely equal, like for this triangle here, where 2 plus 3 equals 5, you have a line segment with no area inside of it. So Heron's formula gave us the correct area once again. It's 0. So to recap, you can use Heron's formula to find the area of any triangle when you know its 3 side lengths. It's a really useful formula to know. In a later lesson, we'll work through the challenging proof showing that Heron's formula is correct.